Today with us, we have a very exciting talk of using the cloud to power virtual reality and gaming on mobile devices. This talk will be given by Dr. Eduardo Cuervo. He's a computer scientist with vast experience in game streaming, computational offload, and virtual reality. He's currently a software engineer in the AR/VR division of Facebook, where he works on enabling the future of work on Oculus headsets. Really cool stuff. Look up his Twitter stuff. He's Cloud Raven. Before Facebook, he was a researcher at Microsoft, where he led the Cloud and Edge Mixed Reality Initiative, focusing on enabling untethered immersive mixed reality experiences, which he's going to talk about today. He has a doctoral and master's degree in computer science from Duke University, and a bachelor's degree also in computer science from Tecnológico de Monterrey in Mexico City. So with that, Eduardo, please take it away.
Thanks, Robert, and thanks so much for inviting me. And good afternoon, everyone. So it is my great pleasure to share with you in about 45 minutes a summary of roughly 5 years of research on a topic that I am very passionate about, bringing high-fidelity gaming experiences to mobile devices, and especially mobile VR headsets. Okay. Virtual reality is an exciting but very unforgiving technology when it comes to resource requirements. When it comes to tricking your brain into believing it's in another world, you either meet the requirements or you're going to get a lot of your users sick. If you want your users happy, you want to deliver experiences with a motion to photon latency of less than 20 milliseconds and a frame rate of 22 frames per second or higher. But that is just the beginning, because truly immersive experiences benefit from photorealistic visuals that are very compute intensive. And a hard truth in life here is that mobile devices cannot meet these demands without compromises, at least not today. And this is the same statement I had like 8 years ago when I started working on this. So why is that? You can say, sure, mobile GPUs and CPUs are advancing. We are making like huge leaps. If you take a phone from 8 years ago compared to now, it can do like things that maybe you could do in like a PS3 or like some kind of like high-end computer from back in the day. The problem is that even if you take a current super high-end desktop computer right now, it's still not quite there where we want it to be. So if you want a truly immersive experience in which you cannot tell the difference between the real world and the virtual world, that's where we want to be, and we are not there yet, even in desktops. And if you look at mobile versus desktop, you will see that the mobile device is trailing behind quite a bit. Why is that? Why do we have this gap? Well, this is actually a fundamental gap between the capabilities of the components of a mobile device and the capabilities of a full-size computer. This is very specific to the GPU more than everything else. The gap is caused by the mobile device form factor, which limits power consumption and heat dissipation. This very fundamental gap is unlikely to go away without a breakthrough technological advance. I mean, you can just see how a modern GPU like the GTX, like RTX 3090, for example, will take like 350 watts, while a mobile GPU will take maybe 4 watts. So it's a big difference in heat dissipation, a big difference in power consumption that is not going to go away. Here I have a set of images from 2010 of Street Fighter 4, because people that know me will know that I'm a big fan of the franchise, so I had to keep it here. But if you want to look at a comparison with much recent titles, you can just Google YouTube, like Witcher 3 PC versus Switch, and you will see how the difference between a mobile computer and a desktop computer is right now. And if you want to look into VR, you can just see, like, for example, how Robo Recall works in PC versus mobile. So that leaves us with like some options. Like the standard option still right now is to use tethered headsets that will give you the better visual quality, that will give you the most responsiveness. But the problem is that it's expensive. You need to buy expensive GPUs, like a full computer. It's not mobile, and it requires, again, a lot of power. The other option, like for example, now with like newer headsets, is to go mobile. So you can have a full headset, a headset that has like all the GPU, CPU, everything built in, and you can get an immersive VR experience. The problem is that here we are sacrificing visual quality when compared to a desktop system. We are sacrificing some responsiveness, but this is more affordable and it's more energy efficient, even though we are still struggling with like having a headset that will last the battery for the whole day. Another approach is to do remote rendering, and this is like something that is more popular now with applications like VR Desktop or like Oculus Link on VR, or things like Steam in-home streaming, for example. This consists of you having your headset connected to your desktop PC through a wireless link, or maybe like a USB long cable. And in this scenario, you will actually send the VR content or the game content as compressed video. This gives us the advantage that you have more mobility than being tethered to a computer, but still you require a big PC, so it's just as expensive, and you will sacrifice some quality and some responsiveness because of the latency in video encoding and the latency of the wireless link. Now, something new that we are seeing now, I mean, it's actually not new. I have seen this like since 2010 with companies like OnLive, but now it's becoming more mainstream. So you can see things like Stadia or Project X Cloud that consist on rendering something in a big computer in the cloud and sending it to you through your ISP. And this is working remarkably nice for traditional games. So like you can stream like your Xbox games or like your computer games from Stadia and xCloud. And it works mostly fine with some sacrifice in, of course, latency and responsiveness and some degradation on quality, which is probably acceptable for some people that don't want to invest in a console. Now, if you think about this for VR, that's a whole different beast. So cloud is not yet good enough for VR. And the problem is the fundamental latency that the cloud has. When in a game you have delay, you may be upset because your move didn't connect when you wanted. When you have delay in VR, you're going to get sick, and that is much worse. Also, VR places more strict requirements than what normal gaming does. So like you need a stereo vision, that means like a pair of images. You need high frame rate, 72 plus 90 frames per second. You need high resolution again to like get this more immersive experience. Now, the question I have been asking since like I started working on this like roughly 8 years ago is, can we leverage the mobile GPU to overcome these limitations? And the answer is yes. So this is the goal I had in mind when I started working on hybrid cloud rendering. The idea is to have something that gives us the advantages, or most of the advantages of a tethered device, and also those of the untethered device, and then some more. We are not there yet, but I have done a lot of work towards making steps that get us close to that goal. So as a summary of the work I have done in this area, I have done work on streaming solutions for 3D in general, Kawaii, a system that reduces bandwidth consumption by up to 80%. At the time, a system that hides the perceived latency up to 120 milliseconds. And there are also like some VR-specific solutions like Flashback that we can use storage and caching to pre-render VR content. There was Iridis that was designed to bring both low latency and low bandwidth at the same time. And Proxy IBR that was designed as an improvement over the techniques I previously described. In the interest of time, I will just go briefly over the other ones, but I will focus mostly on Flashback and Proxy IBR. So for the rest of the talk, I will go first over my 3D graphic streaming systems, then go over Flashback, and then actually I will going to go over Proxy IBR instead of Iridis. I will skip Iridis this time, and then go over some conclusions. So to begin with, let's go for Kawaii, which comes from the Hawaiian word for stream. It's a system that reduces bandwidth requirements through a concept called collaborative rendering, in which part of the rendering effort is done in the mobile device and the rest in the cloud. Then, out of time is a system that hides latency by executing the game of application speculatively in the cloud, predicting user inputs and fixing prediction errors in the device. So let's begin with Kawaii. Kawaii introduced this technique I named collaborative rendering that is designed to reduce bandwidth consumption. In this technique, we run the game at the same time, but with different detail or frame rate settings. And by leveraging the client-side game output, we can reduce the amount of information that can be transferred. The first way to do this consists in having the mobile device render the game at low detail settings, while the server renders at the same scene at the highest level of detail, sending the missing information to the client. So here we have a mobile phone rendering Street Fighter 4 at low quality and a server doing it at high quality. The server will figure out the differences between the mobile version and its version and send the difference. In practice, it works like this. Let's say we have Doom 3. Here we have a low detail version of the game that is so low detail that the mobile client can render it at full frame rate. Now let's see the same version of this frame rendered by the server at the highest settings. The trick here is that the server will render both versions, its own and the client's. And it will compute a pixel by pixel delta on both versions, which will compress as video and then send it to the client. The advantage of this video is that because it has much lower entropy than any of those other versions, it compresses much better than sending the high quality feedback. Now, there is another way to do this. In this case, both the client and the server will render at the highest fidelity, which will, of course, result in the client not being able to render at full frame rate. This is not an issue because the server will provide the missing frames. The key technique here is that the missing frames are going to be encoded as p-frames. Those are transitions frames that only encode the difference between themselves and the keyframes that the mobile device will produce. Because we know these keyframes are uncompressed and perfect, we can be extremely aggressive with the compression and still deliver high quality visuals. Now let's see this in practice, running it on Doom 3 again.
Here we see Doom 3 running on a Surface Pro 3 with high detail settings. The game does not run smoothly because the computer is not fast enough to deliver 60 frames per second, instead rendering between 12 and 20 frames per second. While this frame rate is insufficient for an enjoyable experience, it is well suited to be turned into a wonderful experience with Kawaii's iframe mode. Before showing Kawaii, first let's see how this scene would look like rendered remotely and transferred using traditional H.264 video streaming at 1 megabit per second. Notice the blocky artifacts that appear because of heavy compression. Now let's look at Kawaii running the same sequence on the Surface Pro 3 at 1 megabit per second. With Kawaii, we obtain the full detail of the game at full frame rate. An H.264 stream of equivalent quality would have required 7 megabits per second. Here we have the same scene rendered at a level of quality that the Surface Pro 3 can handle. It is easy to tell the missing details, especially in the textures. While this experience is playable, it is highly unappealing. Fortunately, as we can see now, Kawaii in Delta mode can provide the missing details. Once again, we have high detail mode at full frame rate. While the quality is not as high as that delivered in iframe mode, Kawaii's Delta mode allows collaborative rendering on devices that are unable to deliver at least 10 frames per second in high quality settings.
So I hope you could hear the audio. I was reading that over the slides, but if not, I guess.
Yes, Eduardo, just to confirm with you, the video is coming through great, the audio is coming through great, and I'm really enjoying this talk so far.
Thanks.
Please continue.
So let's look at the results that I showed in the video a little bit more in depth. So this is looking at the iframe and delta frame and delta techniques on that specific video of the Cyber Demon, for those that play Doom. Here we can see in orange, the thin client, that's like the naive version of just streaming the high quality frames. Delta is the first approach I suggested, we like doing high minus low. And the last one is the iframe approach that is sending just a few frames from the server. In the x-axis, you can see quality as measured using the SIMDV scale. For your convenience, I provided a mapping of what that means in terms of mean opinion score. So unacceptable, fair, good, identical. And on the y-axis, I have the bit rate. So this means that going to the top left corner will be worst, and bottom right will be best. Let's look at these 2 points, for example. Here we can see that we can achieve the same quality that we can achieve in thin client by just using about 1/6 of the bandwidth, which is really a lot of savings. Now, taking a detour here, I'm going to now talk about auto time. So auto time was a system we built after building Kawaii, because we realized that, actually like latency is also very important, perhaps more important than bandwidth. So in auto time, we predict the user's input for a very short horizon, let's say less than 120 milliseconds. And we execute speculatively on the server based on that prediction made. That means you don't have to wait for your input to go the server, and then the server executes. It just assumes the input for you using prediction. We found out that for games like Doom 3 and Fable 3, using like a sample of, I remember, maybe 30 users, it was possible to achieve high accuracy just using a Markov model and a Kalman filter. Here we have a chart that we show like the accuracy for different inputs. So like forward, back, left, right, up, down, changing yaw, changing pitch. We can actually have like very high accuracy for 64 and 130 milliseconds. When you push it to 256, is maybe too much. But the important part here is like, it's not like we are guessing your whole playthrough. It's just a little bit ahead of time. And sure, even though our model was pretty effective, that anything below 1 means that they are errors. We need to do something about them. And this is where we apply techniques for scene reconstruction that we are borrowing from computer vision, computer graphics that I will explain now. We also use instant rollback of the execution, in which if we make a mistake in the server, we'll roll back to an August state and we play it back faster than normal. So let's go over the graphics technique just to summarize at a time quickly. In computer graphics, there is a set of techniques called image-based rendering, in which you use images to form a new, you use previous images to form a new image. There are very efficient scene reconstruction techniques within this umbrella of IBR that even thin clients like mobile phones can use to rendering quickly. Something nice about IBR is that because we're using bitmaps, the complexity is proportional to the resolution and not to the level of detail. So as long as you are like doing like, I don't know, like 1K, 2K, the cost is going to be constant, no matter whether you have like very fancy shaders, reflections, etc. And we can use these techniques to reduce the apparent latency and fix mixed predictions in our mobile server setup. In our scenario, we can take a mispredicted frame and its associated depth buffer to show it to the user as the actual frame. But how does this work? Let's say we have the server rendering a view that it thinks is the right view with a predicted position that it just got from the model. So it will render it and it will capture it and sending as an RGB set of pixels, and also a depth map. A depth map is pretty much saying for each pixel how deep we know this pixel is, so like 1 meter, 2 meters, etc. The client will compare this set of pixels and the position the server says it believes it had with its actual true position. If it's the same, it just lets it go. But if it's different, then it has to do something about it. It will use the received image and the depth to reproject those pixels into the right position, matching the actual camera position. Now, there is an issue here. So let's say that we have this frame from the past and we rotate it to the right. We don't have those pixels. And that is an issue because we don't have anything to fill them with. How do we solve this? Okay, we use what is called a cube map. So we expand the view and we render additional views from the sides that will cover the pixels that we may be missing. Now, I don't want to go into too many details on auto time. There is like something we are doing for other types of events, like you shooting a gun, you opening a door, etc. And you can actually go and look at the paper and you can get all the details. But this is like the part of the background that is relevant to the rest of the talk. So I wanted to just cover this part really quickly. So shortly after finishing auto time, VR caught my interest and some of my colleagues' interest, so we decided to apply the lessons learned from 3D streaming to mobile VR. In Flashback, our goal was to support high-quality VR on mobile devices, even if we don't have internet connectivity. So this works actually offline. What is the observation here? Well, we know that mobile GPUs are constrained, right? Like your phone gets hot, and your VR headset gets hot and run out of battery. The mobile GPU is not enough to push all of these pixels. But we also know that storage keeps getting cheaper and more compact. So taking those two observations together, then here is this crazy idea. What if we could render all possible views for fast real-time replay at a graphical fidelity above the device capabilities? Well, guess what? We can't do that. How does this work? We have a pose, and a pose is a position plus an orientation. So in VR, like you can have like an X, Y, Z position, but also you need to have like a pitch, roll, and yaw orientation. We want to map that to the frame that you will watch given that pose. The problem is that there is an infinite input space here. Like you can just move 1 millimeter and move like one tiny fraction of a degree, and you will get a different image. And that will require, of course, infinite storage. Instead, what we do is, let's just take a discretization of the space. Let's say that we sample every meter. So like we discretize on position, not on pose. And we create a cube map like the one I mentioned before in that time that is composed of a cube map for RGB and a cube map for depth. And we cache that. So here's an example of a cache cube map that we will keep in our cache. At a high level, Flashback will work in the following way. Let's say that we have our cache with all of these discretized positions and a cube map or mega frame for each of them. When you are playing the game, the headset will get a pose. And then our component will look for a mega frame in the cache, which then it will be warped using the IBR techniques like mesh warping into something that you can display in the headset. Let's look first at the cache. This is very important for Flashback to be very responsive. Remember that we have very tight constraints here, less than 20 milliseconds, 90 frames per second, etc. So we have first an L3 cache in the SSD that will store all of the cube maps. And we are doing this, we're compressing each cube map as a single frame H264. This is one of the interesting tricks of Flashback. We use single frames so that we can take advantage of the built-in hardware decoder, which is actually very cheap to use in terms of power and also in terms of latency. But the problem with video is that for you decoding frame 5, you need to decode frame 1, 2, 3, 4 before that. But if we have single frames, we can rip most of this, well, not most, a good portion of compression, and also still use the hardware acceleration. This L3 cache will have like all these entries compressed in video. We will have another L2 cache that will be in system RAM and also encoded. Finally, we will have a super fast L1 cache in GPU that is just composed of these decoded megaframes. So in here, you don't even have to decode. It's like really, really fast. And because it's a GPU to GPU copy, you get frames pretty much instantly. So there you go, access times 9.2, 8.7, and 0.35 milliseconds for the L1. So fast retrieval, check. Now, we are caching 3D entries, right? So our position is not going to directly map to something in the cache. I mean, you may have an entry for position 1 meter by 1 meter by 1 meter, but you may be at 1.3, 1.2, 1.0. So you can, if we use a structure that is friendly to spatial caching like R-trees, we can approximate these queries and get the nearest entry in the cache right away. So in exact query matching, check. Now, let's look at pre-rendering dynamic objects. This is a concern because everything I have said before applies to things that don't change. If nothing moves, then everything is good. Your single cache works fine. But what if you want to have people moving, cars moving, you name it? Then you need to cache them separately. And for this, we need a 7-dimensional input space. We need 3 dimensions for the relative position. That means if the, let's say, a car is in front of me, is to my right, is above, depending on what angle it is, because we are doing an image-based rendering, we need to cache a different image for each of these relative positions, and which will, of course, be discretized as well. The same thing happens for rotation. So if the car is like this, it's not the same as if the car is like that. So we need to cache that as well. This is maybe not as obvious like when it's like a rotation in one axis, but if you have like a multi-axis rotation, then things become more interesting. Now, let's say we want this car to be animated or like this person to be animated. So just as like in classical animation, we can have a strip of each animation step, and we can make an entry in the cache for each of these animation steps, given all these other 3D dimensions. So we will have something like this. Let's say like we have like this card, we have like these discretized cameras capturing it, and we will rotate in every possible way the card. So we can create the cache for the card. As you can imagine, this cache will grow much faster than the static cache. So Flashback is designed for mostly static scenes, but if you have like something where like everything is moving like crazy, maybe Flashback is not the system you want to use. So, okay, we have our static cache and our dynamic cache. Now, when we want to put them together, we need to do a composition step. And well, you may imagine that like some other limitation here is that you cannot really have like these specular effects. You cannot have like shadows. You cannot have like lining reflecting on the floor and in the dynamic object. So this is again one of the limitations I will discuss a little bit later. So we decided to evaluate this in a weak device, but for practicality, it's very time-consuming to port a game from desktop to mobile. So we instead like grabbed a computer that really models the weakness of a mobile device. And for you to believe me, I just want to show you this benchmark. We use this HP Pavilion Mini that is just actually weaker than a Samsung Galaxy S6. And there are like 4 benchmarks just to show you that. And both the Galaxy S6 and the Pavilion Mini, by the way, were much weaker than the desktop we were using back then. So this is the Pavilion Mini struggling with this scene. This is, by the way, a free scene from the Unity store. It's called Viking Village, and I have been using it for most of my prototypes for a while. So you can see like the frame rate is abysmal. Like if you wear this, you will get sick. I know because I got dizzy trying to play with this on the device. Now this is with Flashback. Here you can see the dynamic object. You can see the scene moving smoothly. It's actually much more usable. So how does it look in the numbers? It looks like this. We got 15 times the frame rate we got in the mobile device alone. Actually, our performance is very comparable to just like the desktop we had at the time. And a nice bonus is that if you are hitting entries in the GPU cache, Flashback is actually faster than the desktop. Why is that? Because well, you're actually just taking like the access time plus the code time to render. Again, the latency end-to-end is again, much, much lower for Flashback. So for the mobile HMD, because we are on the frame rate, the latency is huge. For the strong desktop and Flashback, the latency is more moderate. And finally, in the GPU, it's really, really low. Now, Flashback is also more energy efficient. Again, it's cheaper in general to use the video decoder than using the GPU. And well, more battery life means like cooler devices that last longer and happy users. As I mentioned before, Flashback has some limitations. One of the main problems is handling dynamic objects. So like if you have 1 or 2, it's fine. If you have like 50, that's probably not going to be that good. And lighting models are limited. Again, as I was saying, especially with dynamic objects, it's very hard to have like some light source in the static cache affecting the illumination of the dynamic object. But also within the cache, let's say that you have like a scene with a sunset and the sun is setting, we will need to cache different entries, like another dimension just for different lighting effects, which will make the cache much larger. And that doesn't mean that this is not applicable. Actually, there are like, it's very common in VR headsets to have mostly static scenes. So if you think about like home environments, like the lobby in Windows Mixed Reality or Oculus Home in Rift or Oculus Quest, and the Vive Home for like the Valve Index or the HTC Vive, all of these environments are mostly static and are like the first window of entry for the device. So having like something really cool there has some value. And of course, we can actually like do things in Flashback to make it support those in the future. So in conclusion, Flashback avoids real-time rendering by pre-generating frames. It supports static scenes and dynamic animated objects. We are bringing with this high frame rate, low latency, and low energy VR to mobile devices. So moving to the next system, after working on Iridis, that I didn't mention, it was something to also improve latency and bandwidth. You can like maybe like see the papers in my page. And Flashback, the one I just mentioned, I realized that improving the quality and fidelity of IBR was really important because we were struggling with like these artifacts when your IBR was not accurate. And these artifacts maybe are not a big deal or as much a big deal in computer games when you have a monitor, but when you have something right on your face, it again makes you feel sick. So there was something to be done about this. So for that, we built a Proxy IBR. Now let me give you a flavor of why we have problems with IBR. Coming back to these slides I showed in auto time, IBR is actually slow on weak devices. I know I mentioned that like IBR has techniques that are fast enough for thin clients, but there is a trade-off. The more accurate you get your technique, the slower it becomes. The faster you make your technique, the less accurate it usually becomes because it's maybe a little bit off topic, but we have a mesh that we use to warp in auto time, and the grain of the mesh determines how accurate are our results. For a very fine-grained mesh, mesh warping can be very expensive. We also have problems with missing connectivity. So let's look at this point. Let's say that you have like this scene that you have here, like the green eye is where the camera was when you predicted your frame. And the black eye is where the camera actually is. So you see in green, you see each of these squares means a pixel that you're capturing. So this green eye is seeing, actually, I don't have it here. So the green eye is like seeing some pixels from the triangle and some pixels from the sphere, but it doesn't see anything about the square. While on the other side, the black eye actually can see the orange square, but we don't have pixels for that, which is a problem. So what happens when we have like this missing connectivity? We don't know what is in between those pixels. Let's say that like, let's say we're looking at the black eye and we have these two yellow pixels we took from the previous image and those two blue pixels from the old image as well. We don't quite know what's in between. So we have a few options. We can say like, I don't know, so I will put blackness, which looks bad. And we can say, you know, actually, let's just combine it with the neighbors. That will give us a blue yellow pixel in between. That is actually not the true as well. And what we have is occlusions. These occlusions is what I mentioned earlier when you don't have pixels to fill in areas you don't know. So the contributions here are that we are resolving these occlusions through a dual view representation, that we are improving render efficiency by using projective texturing, and that we resolve the missing connectivity problem by using a client render simplified geometric proxy for projective texturing. Let's go a little bit into those. Again, resolving these occlusions. These occlusions, when I was mentioning like this rotation in other time, a disocclusion is when your previous view, no, your new view is revealing pixels that were covered in your original view. That is like they are no longer occluded, therefore disocclude. What we were doing before was just a cube map, but now we want something that is more compact, something that covers as little as possible and is robust. That means it covers as much as possible. Cube maps, which we used before, work for this, but the problem is that they are actually giving us too many pixels to the sides. So Outtime was using cube maps. So if you, let's say, like you looked a little bit to the right, you can have the pixels. But if you look all the way to the right, you can also have them. The problem is that your mispredictions are more likely to be small rather than large. So you should optimize for the more likely case of small mispredictions and not optimize that much for the larger case. That means giving more pixels to the near periphery and not as many to the far periphery. In order to do this better, we use a fisheye projection that will cover, again, like 180 degrees field of view, but it's going to sample at a higher level in the center. So to make it clearer, it will look like this. Let's say we have this view, and we are making fisheye. Now we have more pixels towards the center, and we are using less pixels towards the periphery. When we unpack it and keep it into something like a mega frame, it will look like this. Okay, so now we have rotational disocclusions covered. Rotational disocclusions are the ones that are introduced when you rotate your view and you don't have enough pixels, the ones that Outtime handles. Now, that's not the only type of disocclusion. We also have translational disocclusions. That happens when the camera moves to a different place, and then from the new point of view, it can see objects that were not visible before. Let me show you a video to explain. Here we have in black translational disocclusion. So you see, like, you are moving, and as you are revealing the pixels, those pixels cannot be recovered because they were hidden before. This is a kind of disocclusion that actually Outtime wasn't handling. So when you were having like this kind of disocclusions because you were moving too far, actually you're just even moving a bit, it will just stretch the pixels. Now, to make this better, here the proposal is to have a dual view representation. And here I was thinking of something like, let's have a periscope. So the dual view is going to be like this. It's going to sample pixels that are going to be very useful for our future view, and hopefully not being too redundant. So it was like this, like a periscope. Like you put the camera up above to the front, and you tilt it down. So it's kind of like, it's just like, look, let's say like you have a fence in front of you, this periscope will look just above the fence. And actually this heuristic worked pretty well. It will look kind of like this in this scenario. Like you have like This view in yellow is the original view, and the auxiliary view is going to be a little bit up, tilted, and it will look some of the pixels behind the fence. Now, there is some more we can do here. Well, I actually forgot to mention. It will follow the view. Like, it will be like, again, like you have like a stick. Like, let's say like you have a selfie stick with a camera, it will work like that. But it has some redundancy here. Let's say that we want to avoid duplicate data. There is a technique called depth peeling that can help us discard the portions of the scene that correspond to the first layer. It's called depth peeling because it's kind of like peeling an onion. So let's say that you have like this first layer of the scene is the fence. So that layer is going to be peeled off. It looks like that. Everything that you see first is going to be removed, and you see what's behind. This will make these pixels even more useful. So now this we have. This is our fisheye projection. This is the equivalent depth map. And this is our secondary view with its associated depth map using depth peeling. With this combined dual view, now we have this. You can still notice some artifacts. That's what like our users call ghosting, but it is much less perceptible. Actually, I think it's pretty nice. We consider this a vast improvement over previous IBR. But let's look at live in terms of walking through a scene. Look at this video. Look at all of these black pixels in the single view versus our proposal. You can see that actually you cannot see many black pixels, if any at all. In a chart, it actually looks like this. We have some disocclusions, but they are fairly minimal. Now, for the next contribution is the rendering algorithm. That's something we call projective texturing, because we are actually texturing geometry using like these bitmaps. Again, we have the previous image, or like the predicted image and the pose. And we have geometry. What does that mean? Let's say that you have a set of buildings. We will ask the mobile client to render those buildings, but in a very simplified way. Let's say that kind of like Minecraft looking, like very, very basic. So that it's still cheap and it can be done by the mobile device. And we are going to paint on top of that geometry using our bitmaps. The output should be, again, a rendered image that can be used for the mispredicted view to look like what you expect. Now let me show you how it works in. Okay, so let's say that you want to have like to get this pixel from the yellow triangle. You can go to the previous image and use that pixel and paint it over like the simplified triangle. They have like a other slide here for that here. Here it is. So it works like this. We want to do this in the mobile client, right? So I was mentioning that we want to have a simplified geometry. Here we have very basic shapes, but like just to convey what I mean, let's say that you cannot draw a circle because it's too complex. So you draw a pentagon. You look for the pixel in the previous image. But now, because the geometry is not an exact map to what it's actually in the server, you may not get it right. In this case, we got it right. But let's say that we are looking for something more complex like here. Here, actually, we should be rendering the yellow pixel from the triangle because there is actually no blue sphere there. So what can we do? And this is like the tricky part, right? We don't want to render something that doesn't belong. What we do is we're going to look the distance between ourselves and this proxy object and use that to disambiguate which pixel we want to grab from the previous image. So here, if we weren't doing this, we will grab the orange pixel because the previous view actually is seeing an orange rectangle there, which is also not right. So we look at the depth test. We looked at, okay, the pixel I'm seeing is as far as this yellow triangle. The distance between my previous view and the orange rectangle is different. So that cannot be it. So we have to look again. And now we can get the yellow triangle. Something important here is that the simplification has to be engaging. That means it has to be an strict envelope on the object. If it's smaller, like in this case, we're going to make a mistake. Let's say we want to get like this pixel. Because we don't hit the proxy geometry, we are going to go all the way to infinity. So it's like, we didn't hit anything, so this should be the color of the skybox when you actually hit the blue circle. But if we have it like this, then you will actually hit it and get the right value. So to summarize, the reason for us to have a proxy geometry is because you want to disambiguate when you don't know if you should grab a pixel or not by using the depth from your hard truth camera and that proxy geometry. So how does it look in practice? This is how it looks without, by using like a naive geometry simplification that is not engaging, without using a depth test. So what happens here? You are trying to grab pixels from the previous image, and you cannot tell if the water belongs in the background or belongs to the object that you're hitting. So that will be like the case when it goes to infinity and you grab from the background. And the other problem is like the nose. This is when like the geometry is not engaging. You just went to infinity and grabbed a pixel from the background and put it in place of the geometry. If we have a depth test, then we can disambiguate when the water actually, when the water should be in the background and when it should be like part of our geometry. But we are still missing the nose here because the geometry is not engaging. So it's like goes to infinity. Now this is our simplification. No depth test, again, we have the water, but everything together, we have the nose of this Viking ship. And we also have, we don't have like water crawling into the geometry. Finally, I want to go over how we are resolving missing connectivity. We are using a geometry simplification, which again is what I mentioned before. We are reducing the number of triangles. And this is important because we want to render this on a mobile device. This will be a geometry only, so it will have no textures. We only care about the geometry. So this can be very cheap, but still, if you can reduce the number of triangles, it's going to be much cheaper for the mobile device. I'm actually going to go a little bit quicker over this. This is the way that is normally done. What we are doing is a more stable simplification in which we voxelize the mesh, we float fill it, and we run marching cubes. Again, like I cannot go into much detail into here, but you can go into the paper and see exactly how this is done. And we simplify at the end with Blender. We will get something like this, that is watertight. That means if you were to 3D print it, like it will not get water inside. So this is an example of how like the original mesh looks versus the simplification of level 1 and just the maximum simplification. What are the results we obtain here? Well, we tried this on a very weak compute device. That is a compute stick from Intel. Actually, now like it would be like ridiculous to try to play with it, but a few years ago was still kind of reasonable. So I am comparing here several techniques like mesh warping, homography, quad tree, point splatting, iterative image warping, and hours. Maybe like some of them worth highlighting are homography, which is like modern headsets use, and mesh warping, which is what at the time used. So as you can see, like we can actually like do much faster than mesh warping, and we can do close as fast as homography. Homography is actually not using depth, so it's not as good with parallax. So we are getting parallax, at almost at just a little bit higher price than doing homography, which is great. Again, the results are also very good. We have again an SSIM versus frames per second graph. Actually, this is like a DSIM, so it's like dissimilarity. The best results will be here towards the top and the right. Here we are doing much better than homography in terms of quality, and we are doing much better than mesh warp in terms of performance. So this is the compute stick doing mesh warping, really, really bad. This is using a coarse mesh. This is doing point splatting, another technique. This is with an homography. I mean, maybe it's like too fast, but there is like no, I mean, I don't know if you can notice, there is like no parallax here. And this is another one, iterative image warping, quad 3, and finally hours. Our users were very happy with the results, but we have some limitations. I mean, just as in Flashback, and this is like something very common to IBR and in general to scene reconstruction, is that it's very hard to have dynamic objects and view-dependent effects. So view-dependent effects are specular effects, like you have like reflections, you have shadows, you have smoke, transparency, semi-transparency. All of that is actually very hard to do with these approaches. And we discussed in the paper some of the techniques that we can use to make it better, but it's an ongoing challenge when you are talking about image-based rendering in general. So in conclusion, Proxy IBR gives an improvement over image-based rendering for scene reconstruction. We get faster rendering and higher quality images than previous approaches like mesh warping. And most importantly, it runs on low-end hardware. I mean, this is like a really, really weak PC. It's like a Celeron with a super old Intel GPU that is running this kind of VR, which is remarkable. So in summary, I presented 4 techniques that have each of them different pros and cons. So Kawaii was very good at delivering low bandwidth, doing offline support, dynamic objects, clear effects, VR quality. And we have Autotime that is more about low latency, Flashback that is all about offline, Proxy IBR that is more about improving the online support of IBR. Finally, summarizing and wrapping this up, offloading VR to cloud is not a straightforward solution because we are very sensitive to latency and bandwidth is expensive. Here I presented system-level techniques to mitigate those problems, in which we can reduce bandwidth by up to 7 times. We can hide up to 128 milliseconds of latency. We can cache most static scenes and yield desktop-like performance. And we can use projective texturing and dual views to deliver high-quality IBR. So with that, I'm happy to take questions. There is my webpage if you want to see some of these papers, my email if you want to contact me. And of course, the assets from SF4 and Doom 3 are copyright protected by their owners. So thanks.
Eduardo, great talk. Wonderful. I think everybody really enjoyed that. And you drew quite a crowd as well on YouTube. So anybody, if you'd like to type your comments, I'll actually read the comments that are on YouTube, but on Zoom, I'll actually call on you to speak. So Ali, Curtis, Venkatesh, and Jinhan, since you typed in your questions, I will call on you to unmute in that order, Ali, Curtis, Venki, and Jinhan. But before then, I'll start us off, actually. So I think one of the really cool things you started talking about was bringing up the challenges of dealing with VR compared to screen-based games, right? Whereas VR, you are actually worried about the latencies that are involved. If you want to scale these challenges and maybe opportunities to optical see-through devices like HoloLens and other holographic devices, do those challenges, I guess, of latency probably become exacerbated with the need to align with the physical world? Or are there other opportunities that you see that could kind of mitigate those sorts of challenges?
So actually, AR is interesting because the challenges and the opportunities are different. Yeah. So if you think of something like HoloLens, where you have you want to see like synthetic objects overlaid on top of the real world, One of the opportunities is that because you have the real world as your anchor, actually you are more tolerant to simulation sickness. So you are less likely to get VR sickness. That means you can tolerate more glitches in the synthetic object without getting sick.
Mm-hmm.
Now, timeliness is still very important because let's say that you are actually like handling a synthetic object with your hands. If the object has high latency, it will cause a disconnect. Like let's say you're handling a ball and you move it with your hand. If the ball doesn't attach to your hand, it will feel wrong. So in terms of sickness, it's better, but also the requirements are still high. Some of the opportunities, though, is that in VR, you are responsible for rendering the whole screen. So a lot more pixels. In augmented reality, you are only doing a few synthetic objects. So they are smaller. This is good because you don't need to cache, or you don't need to stream, or you don't need to pre-render all of this, everything in the scene, just this specific object. So you can actually put more detail or put more resources into just those. So that's a very interesting opportunity. Now, challenges again. It's more important in augmented reality for the object to be consistency with spectral effects, reflections, etc., that come from the environment. So I don't know if this answers your questions. I think it's a different problem, and you can take advantage of some of the relaxations. So you can definitely, if I were like to tackle this problem, I will go deeper into, okay, let's take advantage of like these being very small. Let's take advantage that actually I have more of my video decoder and encoder free. I can use more pixels for representing these. Mm-hmm. So I will go in that direction.
Yeah, very nice insights there. Ali, do you want to unmute and ask your question next?
Yeah, do we go in linear order of the questions asked?
You can ask whichever one question. Pick one, your favorite one, and ask.
And that's tough. I have quite a few questions for you, Dr. Cuervo, but if I had to hone in on one specifically, in this talk, you've shown several works that introduce new approaches for encoding and decoding frames to improve the graphical quality, responsiveness, and energy efficiency when rendering content on mobile devices. At least these were some of my takeaways. And I'm curious, when it comes to the holistic picture you have for the hybrid cloud-based rendering pipeline, are there specific ideas or approaches that you think are underexplored for the different stages, namely being the rendering, encoding, transmission, and decoding procedures?
So let me see if I get your question. You are like talking about like how to put everything together, or you are thinking more about like, is there like any of these aspects that can be like, that can be dig deeper?
Yeah, it doesn't have to be like the whole picture, but even just specific stages that are ideas you've been entertained by, but you haven't seen explored by other researchers as much.
That's an interesting question. I think what Robert mentioned about like looking into this for AR, I think it has still been a little bit underexplored. Something that I believe is going to be interesting is whether we can use deep learning in the picture. So you can use deep learning to fill maybe these occlusions or to maybe undersample. So like I think that like a big opportunity here, but I'm not sure it has been explored too deeply. But it will be like something I will be interesting. I will find interesting to look at.
Duly noted. Thank you.
Curtis, you want to ask your question next?
Yes, thank you. So this was extremely interesting from like a marketing sense of like how this could change the market. So I really wanted to see, get your take on how do you see these changes changing the market of video games in general? Specifically, do you think that we'll be seeing lower fidelity games, or a decrease in assets, I should say, for higher fidelity games? Or can't even remember what the other part of that question was. But
I think Curtis, I can read off what you said as well.
Thank you.
You were asked. Curtis was asking a quite nice question. How do you think this will change the video game market with VR? Will we see a decrease in the game world to allow for a higher fidelity, or an increase in the assets? And then, do you see this perhaps taking VR into the mainstream market with a lower cost for entry?
So I can share like talking from experience, some of the challenges. I guess that can like also like go into like the previous question as well. Some of the challenges to bring this kind of technology into the mainstream is that it has some requirements, right? Like something we require to make all of this work is we need to make changes to, in most of these cases, we need to make changes to the game engine, or we need to have like simultaneous implementations of the game in mobile and desktop. And this is like something I'm seeing more now. So I am seeing the same game ported from Xbox to Switch, or the same game ported from Rift to Quest. So I think there is an opportunity there, but the effort is still done like in a very manual fashion still. So I think there's like a large opportunity for people building engines to design them in a way that they will be amenable for these techniques. And if that were to happen, I can imagine seeing games that are more dynamic in the sense of the requirements they have, so that they can be more easily purposed. When we get to that stage, then it will also be easier to have games that can be run offline at low quality and online at a high quality, games that will support deterministic execution, games that will also have like more built-in support for speculation, for example. So I think it is interesting, like the ball will be within game engine developers to embrace these techniques and actually release them. So I don't know if that answers the question.
Yeah, I think it does. Yeah. Thank you.
And similarly, a question from YouTube that I'll draw, Walter Javier Aparici says, where do you see the future of this technology going? And I think you're kind of answering in that thread. Where do you see the future of it going?
Yeah, I feel like a critical step here is to rethink how we are doing game engines to deliver games and forget about the capabilities of the device. Imagine that you can have like a game for like, I don't know, like PlayStation 4, and then like PlayStation 5 comes up, and you can have a subscription model that gives you better graphics as you go. But if you are disconnected, you can still fall back to your old model, right? And you can have like the same game delivered for a Switch, for a PC, and you can get the native device capabilities, or you can upgrade. I think that will be a way into which you can have like more like a model of like build once, run everywhere. So I am really very aware that will require a lot of effort, but if it's done, I think it will be worth the price of entry.
I like that take a lot, Eduardo, because you're building in this robustness in that idea then, that if you are disconnected from the cloud and aren't able to take advantage of the techniques you introduced here, there's still something there.
Right.
Venkatesh, you want to ask your question?
Yeah. So hi, my question is more on the motion to photon latency and the simulator sickness. So recently, I tried to test myself, like how much time I can be in the VR world, like by wearing the Oculus Quest, and I could be I lasted for like 30 to 40 minutes, like, and not more than that. So how do we build future VR devices so that we can actually wear these devices and stay in that VR world for like several hours? Like, can we?
Yeah, so I mean, this is very tricky, because really what you are doing is you are tricking your senses into believing they are somewhere else, right? So you get like some of these simulation sickness when there is this disconnect between what your brain expects and what your brain receives. And I actually have a paper on this, and I gave a talk about this like a couple of years ago. And if we really want to get to the point, at least visual, that your brain is fully tricked, like you need to have like a super high resolution, you need to have like a frame rate of like 1,000 frames per second, and we're still far from that. And that's just visual. So if you start like thinking, okay, you need to stimulate like your vestibular system, like your ears, so like you need to make sure that like when you move, you feel like you are moving, and you need to introduce touch, and everything has to come together so that you don't feel this sickness. Now, the good news is that that's the point where you cannot tell the difference. But as we keep improving resolution, we keep improving frame rate, we keep improving haptics, we keep improving like ways to have motion without actually physically moving and you're still feeling that you're moving. All of these will decrease the amount of simulator sickness you get. Something else that also causes sickness is when, I mean, like you are focusing on a screen, but your eyes are used to focus at different distances, right? So like things like varifocal devices will also like help there. So summarizing the answer, there is a lot to be done there. But if you compare an Oculus Quest or a Valve Index to an Oculus DK1, you will realize that like the time to sickness is much larger now than it was like 5-6 years ago.
Mm-hmm.
Interesting. I think that's a great take, Eduardo. And that there are some YouTube questions as well. I'm going to combine these from Melasham Desari and Santiago Garcia. They're asking about what the bottlenecks of VR applications are today. Is it network or compute capacity? Is it a hardware-oriented problem or software-oriented? What are the challenges in the future with faster hardware becoming more accessible? And Quest 2 is taking advantage of these Snapdragon XR2s and whatnot. What's the future outlook there?
So in general, when it comes to mobile devices, like the main challenge is still the battery and power, right? But as I've seen, battery hasn't really improved that much over like the last 23 years. So given that that's maybe not going to change for some time until there's like a breakthrough, then it falls into the other components, right? Like some big problem that there is thermal, right? Like sometimes even if your device can do something, you cannot really push it to the max because it will overheat. And so thermal limitations, of course, like the GPU is still a bottleneck if you want to get like crazy high frame rates, crazy high resolutions. But it's more like it's a very holistic thing. But I will say like battery, thermal, and GPU will be like maybe like the main components.
Mm-hmm. Yeah, I think I can agree with that. Jinhan, do you want to ask your question? And then I think we'll close it out.
Yeah, sure. Actually, I think my question is kind of answered because it's also about like the future of the Proxy IBR project. Because I think for VR, there's a specific feature that the occluded regions is actually known because the scene is actually predefined, right? Or pre-designed. So is it possible to utilize this kind of specific feature to further eliminate those kind of ghosting artifacts that you had in the like Proxy IBR project?
So I mean, even if you will know even if you know the geometry in advance. I mean, that's what we're doing in Proxy IBR, right? We have like the geometry known to us in advance, and we have it in the mobile device. That helps us to reduce the occlusions. But what you don't know in advance is the motion path that the user will take, right? So even if you know the scene, you don't know if the user is going to turn back or move right or crouch or jump. So that's where your occlusions come from. And of course, you cannot have like the scene cached in your device. You cannot have like the scene running in your device because at that point you don't really need to offload anything, right? So what you are offloading is like the expensive part of the rendering pipeline. So like rendering textures, rendering special effects, all of this is expensive, right? So this is the part of the rendering process that you want to offload that you cannot have locally. The scene, you can have it locally as geometry, as we do in Proxy IBR, and that helps disambiguate when you have these occlusions. But I don't know if I missed your point, but you mean that like you have some situations when you know the motion path? Because yeah, in that case that would help.
Yeah, actually, I think maybe it's very interesting to integrate machine learning into this kind of VR context, right? Because recently I've seen like papers in CVPR that they're guessing like those occluded regions in actually real world, and it's actually doing really great. So I was wondering like if there's any opportunity in this also, because generating ground truth in this VR setting is actually very easy, right? Things like that.
Absolutely. There is definitely work on like using deep learning to fill the gaps. So it's not like you are predicting the excluded region and assuming it in advance, because that actually will be like you are not predicting the excluded region, you are predicting the motion. So for example, if we take out a time, like we can, I mean, we were using like very simple models of like a Markov model and a Kalman filter just to predict moves in a 3D game. Now, like with modern games, actually, I think this will be much more complex than Doom 3 or like Fable 3. But also with deep learning, we may have a better chance of getting a better estimate. And of course, if you have like a good estimate, a good guess, there is no misprediction. And if there is no misprediction, there is no disocclusion. So yeah, that would be ideal. That would, let's say that we have like a 0.99999 prediction rate. Even if you have very bad exclusions, they will be like so far in between that it may not matter.
Yeah, cool.
Well, yeah, thanks, Eduardo, for your very illuminating Q&A feedback. Everyone, let's give him a virtual round of applause. Like, wonderful job, Eduardo. We really appreciated your talk. Everybody else, thank you so much for joining us at this Digital Culture Speaker Series, and we'll see you again next week.
Thanks, Robert.
Hey, Kevin, how's it going?